Hello, everyone. I'd like to thank you for joining us for this webinar. My name is Kristen Johnson, and I'm the Sustainability Technology Manager with DOE's Bioenergy Technologies Office, and I'll be moderating today's webinar. So to begin the webinar, I'll provide a brief overview of the Bioenergy Technologies Office, which will be followed by presentations from Virginia Dale from Oak Ridge National Lab and Christina Negri from Argonne National Lab. So just a few logistical items before we get started. Please record any questions and comments you might have during the webinar and send them to eere_bioenergy@ee.doe.gov. As a follow-up to the webinar, the presenters will provide responses to selected questions. And all slides from this presentation will be posted online at this website here. And for any general questions regarding the Bioenergy Technologies Office, please email that same email address shown on the screen. So I'd like to remind everyone that this is part of the Bioenergy Technologies Office ongoing webinar series. Our webinars cover many of the office's activities and feature hot topic discussions that are relevant to the development of renewable fuels, power, and products from biomass resources. And more information can be found on the website link shown here. The mission of the Bioenergy Technologies Office is to accelerate the commercialization of advanced biofuels and bioproducts made from the nation's renewable and abundant biomass resources. Developing a robust bioenergy industry provides multiple benefits. It enhances U.S. energy security, reduces our dependence on oil, provides environmental benefits, including reduced greenhouse gas emissions, and also creates economic opportunities across the nation. So I'll provide a little bit more background about our office's activities, shown on the next slide. Our office's activities span the bioenergy supply chain. Our feedstock supply efforts focus on developing cost-effective integrated logistics systems. So this includes growing, harvesting, collecting, storing, pre-processing, and transporting high-quality feedstocks to biorefineries. Our conversion R&D program is focused on developing commercially viable technologies to convert terrestrial and algal feedstocks into liquid fuels, as well as bioproducts and biopower. And the demonstration and market transformation program is focused on demonstrating and validating technologies through successfully constructing and operating pilot, demonstration, and commercial scale integrated biorefineries. And we also have cross-cutting programs in the areas of sustainability, strategic analysis, and communications. So because today's webinar is focused on sustainability, I'd like to share a little bit more about our goals in this area. Our office is committed to understanding and enhancing the positive economic, social, and environmental effects and reducing the potential negative impacts of bioenergy production activities. And it's important to stress that we take a holistic approach that considers all three dimensions of sustainability, and this includes economic, social, and environmental dimensions. Next slide, please. So given the environmental theme of today's webinar, this slide shows a snapshot of the activities we've been supporting in the area of environmental sustainability of bioenergy. So for example, we work with a range of partners to analyze life cycle greenhouse gas emissions and air pollutants across the full bioenergy supply chain. We also support the development of strategies and tools for enhancing soil quality, as well as landscape design approaches that increase biomass production while maintaining or enhancing ecosystem services, as well as food, feed, and fiber production. We've been supporting analysis and research into the water consumption of bioenergy production, and we also continue to investigate ways that bioenergy crops can improve water quality. We also work with diverse experts to understand and promote practices that conserve wildlife and biodiversity. So during this webinar, you'll hear from two projects in our sustainability portfolio that are advancing a number of these objectives. So with that, I'd like to turn the floor over to Virginia Dale from Oak Ridge National Lab.
Good morning. It's a pleasure to join you on this beautiful Earth Day. At least in Tennessee, it is a gorgeous day, and I hope it is where you are located. I am going to be talking about some work that we have been doing over the past 4 years, funded by the Department of Energy's Bioenergy Technologies Office. And as you can see from this slide, I've had lots of collaborators, and I want to be sure to acknowledge them. The next slide highlights some of the discussion points that I want to make today. In particular, I want to emphasize that the assessment of sustainability needs to look at cost and benefits and requires common understanding of what we mean by sustainability as well as measurable indicators. And we start with the Brundtland approach that environmental sustainability is the capacity of an activity to continue while maintaining options for future generations and considering environmental systems that support that activity. But we want to focus on measurable indicators of this. We also want to emphasize that landscape design for sustainable energy is a pathway forward that can be effective, and it will need the engagement of stakeholders from the local region as well as use adaptive management. So we build from the perspective of William Bruce Cameron, who said that not everything that can be counted counts, and not everything that can be counted should be counted. So we want to focus on what should be measured. We have adopted the overall approach shown here, where we want to identify what key indicators are for making progress towards sustainability, establishing baselines and targets, evaluating indicator values, identifying trends and evaluating trade-offs, and developing and evaluating best practices. You can see that we've checked identifying indicators. Can you go back, please, Erica? Because we feel that we have done that, but we have tested the baseline and indicator values and trends for a study in East Tennessee I'll talk about, and reviewed the best practices, and we want to move ahead completing this circle by applying it to other locations. Now the next slide shows a cartoon that we developed in the 1980s that really pitted, in some sense, the forester against the ecologist. They were shown on opposite sides of the tree, and you can see where the tree might be falling. But because of work that's been done in bioenergy as well as other areas, in recent years we've come to realize that these are not two actors on different sides of the tree, that sustainability should be a perspective that considers all aspects of the cost and benefits and looks at them together. So this is an old perspective, and we think that focusing on bioenergy sustainability will help bring together these disparate views, and has done so. But when you look at the many, many initiatives that are exploring indicators for assessing sustainability of bioenergy, you see they are quite diverse. But also when you look in detail at these, you see that the implementation is limited by the indicators being too numerous, hundreds in some cases, too costly, too broad, and often too difficult to measure. Furthermore, some of the indicators focus on management practices, although we don't really have the information about what practices are sustainable. This is one of the reasons that VITO is supporting the many efforts they are doing, is to find out what practices really are sustainable. So working with many others and doing a careful literature review, we have identified 12 categories for indicators of environmental and socioeconomic sustainability. On the left are the environmental indicators of greenhouse gas emissions, soil quality, water quality and quantity, air quality, biological diversity, and productivity. And on the right are 6 categories of socioeconomic measures of sustainability. But what is key, and I'm going to talk about these in detail, what is key is that we recognize that measures and interpretations are always context-specific. That means specific to the place, to the time, to the type of energy being produced, and to the feedstocks being considered. To look at the measures of environmental sustainability, I'm showing you this slide and emphasizing that for each of the categories we have particular indicators, like for soil quality, the first one is soil total organic carbon, and we have the units for those. we think the units are critical because that makes it very explicit what we are measuring. So we have 4 measures of soil quality. And in each of these, we've tried to target measures that are specific to how bioenergy might be affecting the environment. And we have tried to think about what could be measurable and meaningful in these cases. So we have measures of soils, of water, of greenhouse gas. Biodiversity is a particular challenging one, so we focused on the taxa of special concern. This might mean the species, it might mean the subspecies, and by saying special concern, we're not only focusing on rare or endangered species, but also species that, or groups of organisms that might be of special concern for recreation, for economic value, and then secondly, the habitat of those taxa of special concern. Of course, air quality is important, and we focused on 2 particle size distributions because it is more common to measure the larger particles, but it's the smaller particles that really can affect human health. And of course, productivity is important as well. In terms of the socioeconomic indicators, again, we have 6 categories. Social well-being includes employment, household income, work days lost due to injury, and for each of these, the attribution to bioenergy is what is going to be critical. Food security is a challenge, and that's why it is not shown in the darker blue. There's not agreement among the research community as to how to measure this. We measure it as the % change of food price volatility that is due to bioenergy, and several groups agree with us on that. Energy security is another important category. External trade can be extremely important. Of course, profitability, often measured by return on investment or net present value, is important. Resource conservation is also critical. When we use bioenergy, we have to think about how that relates to depletion of non-renewable energy resources that might occur, for example, via replacement of non-renewable energy resources. So we also look at the fossil energy return on investment. And social acceptability may be one of the most critical factors, looking at public opinion and transparency, but in order for those to be valid measures, we have to have effective stakeholder participation in the activity and also consider the risk of catastrophe. So with many bioenergy activities, it might be the potential for fire, and that's in contrast to a potential for an oil spill, for example. The next slide shows how we intend to interpret these across the entire supply chain, looking at feedstock production, logistics, conversion. In this case, we're talking about biofuels, so we look at the distribution of that fuel and the end use, and that might be affected by engine type and efficiency, as well as blend conditions. When we apply this to bioenergy, the supply chain is a bit different, but the concepts are generally applicable. And the next slide is a bit complicated, but if you look in the lower right, we have shown the environmental categories of indicators in green, and that's the top row above, and then the socioeconomic indicators in yellow. And what we've done is distribute these categories across the entire biofuel supply chain. The point being that you see lots of green, that is the top row, and lots of yellow. We've learned from this analysis that have relied again on in-depth literature review that neither environmental nor socioeconomic measures of bioenergy sustainability fall within any one part of the supply chain. It's not just related to feedstock production. We have to look at these environmental and socioeconomic aspects across the entire supply chain. And we've taken steps to look at these with regard to particular bioenergy pathways or particular locations, because as I've said before, this is always context specific, which is the point of my next slide as well. When we take this approach and adapt our suite of indicators to particular contexts, we try to use this set of 35 indicators as a starting point for the sake of efficiency and standardization. But we are aware that particular systems may require addition of other indicators, or because of budgetary or other reasons, we may require subtraction of some of the indicators. But We'd like to have all of these measures on the table, so even if we don't go through the process of acquiring the data or are not able to acquire the data, we are aware of the potential impacts. And we know that some indicators may be important for different supply chains, and that the protocols for their measurement must be context specific, but we'd like to have them interpreted in view of broader ways to establish and measure these indicators. Because there are so many of these indicators, we've also developed a framework for selecting among the 35 potential indicators, and that is shown here. So first off, we look at the goals for the bioenergy system, examine the context, that is the local region, who the stakeholders are. We identify and consult those stakeholders. And these first three steps we've given within a broader box because together they help us identify and assess necessary trade-offs. It may be monetary trade-offs, it may be in the time or how we do the analysis. And then we determine the objective for the analysis. With that in mind, we can then select a specific criteria for indicators and identify and rank indicators that meet those criteria, looking at information that's available or the resources that are needed to collect or then acquire the data. This allows us to determine the baseline and targets and compare those two values for the indicators and conduct an assessment that leads us to step 8 of identifying gaps in our ability to assess goals and objectives. And then to 9, if the objectives are not achieved, we may have to go back and go through this process again to step 5 or to step 10, where a key result should be identifying lessons learned and good practices for this particular system. A critical step is feedback that supports continual improvement, and that feedback could go to definition of goals, thinking about our context, or consulting stakeholders. So this is the process for implementing part of the approach. And we have moved ahead to think about, it's fine to move to the next slide. We've moved ahead to think about how sustainability benefits of switchgrass can be evaluated using this approach. We've noted that, of course, the crops are appropriate for different conditions, and when we have looked at switchgrass, we've done it in East Tennessee, where it is a native C4 perennial. It can readily be grown on marginal lands and rotated with other crops, and in fact, crop farmers in East Tennessee have had a difficult time because it is not a very productive locality, and our extension agents are thrilled, to put it mildly, that they can have another crop to offer farmers. Depending on management, it can provide an excellent nesting and invertebrate habitat. The root mass can reach 8 dry megagrams per hectare. It's an excellent carbon sink. It requires lower fertilizer application than corn. It has great infiltration. It decreases wind flow and evapotranspiration. It has many benefits for this region. So therefore, we've moved ahead to look at ways to assess the multiple effects of bioenergy choices focused on this East Tennessee region. The image that you're looking at is a facility in East Tennessee that is using switchgrass to produce bioenergy, and we have developed an optimization model that identifies ideal sustainability conditions for using switchgrass for bioenergy for this area. The switchgrass is planted within a 10-county area around this facility. Our spatial optimization model identifies where to locate the plantings of bioenergy crops given the needs for this refinery in Vonore, Tennessee, and we consider both farm profit and water quality constraints. I'm going to go through the optimization model and then talk about the results that have been analyzed by the actual plantings that were done that followed our recommendations from the model. The way this optimization model was done is that we had several objectives to look at the location of plantings that could improve water quality and increase profits while achieving the feedstock production goal for the particular facility. This first histogram shows the run where our goal was to maximize nitrogen reduction, and it shows the % of goal that was achieved. So for this example, red is reduction in nitrogen. By definition, we ran it to maximize nitrogen reduction, so that goal is reaching 100%. The other ones fluctuated, so we got up to about 85% of total profit for that run, and a little bit lower than 100% for nitrogen, phosphorus reduction, and reduction in sediment. But now look at all of these different scenarios that we ran. The maximized profit scenario is the fourth set of histograms, and you can see, as defined, we achieved 100% of our goal of profit maximization, so the blue line's up to the 100% line, but we didn't do very well in the other categories of reducing nitrogen in red, reducing phosphorus in green, or reducing sediments. Interestingly enough, is to compare this to the far right set of histograms, the balance scenario. So we wrote our optimization code so that we balance the profit and the water quality, and we did pretty well in all of these categories. Now, when we show this to farmers in the region, they say, well, the balance looks good, but we don't want to have any reduction in our profit. So this speaks to the need to have incentives and maybe even monetary incentives for achieving water quality benefits. We were able to do this work in East Tennessee because the governor of the state guaranteed a price for switchgrass, so the profit motive was pretty strong because the value was strong. I want to point out that the land area recommended for switchgrass in this model was only 1.3% of the total area in the 10 counties surrounding this facility. So it was a very small area, but with this balance scenario, we could have benefits. So the next slide shows that what was actually done in the field was that when our colleagues at the University of Tennessee established the contracts for planting switchgrass, they used our balance scenario. And then subsequently, we used a multi-attribute decision support system to compare sustainability of 3 scenarios in East Tennessee. This work required great support from our colleagues at the University of Tennessee and other regional universities that are funded by the Southeast Partnership for Integrated Biomass Supply Systems. This is a USDA-supported project that did an excellent job collecting the data that we needed. The next slide shows the results of this case study applied to Tennessee. And the way that you read the chart is shown in your lower left, where the top of the triangle is environmental sustainability, and then on the right we have economic sustainability, on the left we have social sustainability, and the center point of the triangle represents the lowest possible rating, with the outer edges representing the highest rating. And so when we look at these 3 scenarios, which were no-till switchgrass, tilled corn, and unmanaged pasture, and we went through the multi-attribute decision support system, we came up with the following results: that the no-till switchgrass did very well for social and environmental, but not so well for economic sustainability. The tilled corn did poorly for environmental sustainability, medium for social, and much better for economic sustainability. And the unmanaged pasture did very poorly for economic sustainability. And the next slide shows that if you look at the details that go into this, and again, the key to the chart is on the left, where you have the environmental indicators at the top and the socioeconomic indicators next. And then the next slide shows that the environmental categories for the no-till switchgrass at the top do pretty well compared to the tilled and the unmanaged pasture. And those were summarized in the prior slide. Now, the next slide shows the approach that we want to be considering to look at systems as an opportunity to design landscapes that add value. And this cartoon shows that this is looking at biomass as it can be grown and how it affects the entire community. We held workshops on the landscape design approach that Christina is going to be mentioning shortly, and subsequently a small group of us came up with this diagram that indicates what we mean by the landscape design approach: to first establish goals for the context, secondly, ascertain constraints and opportunities, thirdly, identify optimal conditions, fourthly, evaluate and select options. Number 5, to monitor the outcomes and to adjust the decisions as needed. So this whole process involves stakeholder engagement and adaptive management. But we think with this approach, we can really move toward sustainable bioenergy. Finally, I want to mention a paper that Bruce Dale led that looked at how the scientific community should take a closer look by reviewing key assumptions underlying biofuels and carefully consider the alternatives. The status quo on the left is shown in brown because it is a fairly unsustainable situation of using fossil fuels. But on the far right, you can see that sustainably managed, and we're in the process of defining that better, bioenergy crops could actually reduce greenhouse gas emissions, increase biodiversity and wildlife habitat, increase food security, increase soil organic matter, increase rural development, reduce soil erosion, and reduce fertilizer use that would result in improved water quality. So moving toward this is a real possibility, but we need context-specific plans to do that. And finally, the recommended practices that we have come up with are first to avoid negative effects. That means identifying and conserving priority biodiversity areas, applying location-specific management of biofuel feedstock production systems, attending to site selection and environmental effects in the selection and location of the feedstock, the transport, refinery process, and then the final transport, monitoring, assessing, and reporting the key measures of sustainability, attending to what is doable in a particular situation. Don't have goals that won't meet the particular context. Communicating the opportunities and concerns to the stakeholders and getting their feedback, and then employing adaptive management. That means you change if you find a better process as you move forward. So I want to thank you for the opportunity to talk to you. We have a website that gives a summary of some of the work that we've been doing, and I would look forward to having any questions that might be forwarded to EERE.
Great, thank you so much, Virginia, and we will transition now to Christina Negri from Argonne National Lab.
Good afternoon, everybody. I am Christina Negri. I'm an agronomist with Argonne National Laboratory. And first of all, thank you for attending this seminar. Following Virginia's presentation, I will go on to discuss a practical example of a proactive design that we have in the works for sustainable bioenergy deployment in the agricultural Midwest of the United States. Next slide. When we think about bioenergy and agriculture, we know that they are intrinsically connected. Both have been part of our history from time immemorial, and as a consequence, when we think about the sustainability bioenergy, we really have to think about the sustainability of also agriculture in general. Thinking about the challenges that lie ahead for society, which are providing food, feed, energy, fiber for a growing population. We also need to conserve soil, water, biodiversity. And in addition to that, we really now think about resilience to climate change and to decreasing greenhouse gas emissions and other environmental externalities. So agriculture as well as bioenergy has a long bucket list of things that need to be worked on. These challenges demand a rethinking of how we use the resources, and those questions that you see on the screen: is there sufficient land for bioenergy? Is land for food and conservation impacted from this development? Do we have the right crops, etc.? Are all questions that apply also to agriculture. And so our approach is that thinking holistically about these two parallel or interconnected systems is the way to go ahead in looking at deployable systems. Next slide. And for this purpose, we have been thinking and working on designing landscapes which includes sustainable bioenergy. To do this, as Virginia mentioned in her presentation, we really require a change in perspective from a generic development like that Brucedale slide that Virginia presented to a targeted effort, and also to the leveraging of specific traits of bioenergy perennials, bioenergy crops which are typically perennial, make them different from row crops and become tools for the environmental restoration. So you see for a few examples in that slide. For example, deep-rooted perennials can be strategically grown to address nutrient loadings from agriculture in buffer strips. They can scavenge nutrients from row crops and be effective environmental ameliorators. If we think about a water quantity, we can work through hydrological modeling and design, and we can target specific water budget and plan for water resources in a sustainable way. We can also prevent grassland conversion and deforestation through sustainable intensification on farmland. We don't really need to go and use land, it's grassland or forest. We really want to think about how to get the best out of what we already have in the cropland. For instance, we can use underproductive land for a more appropriate crop and thereby increases productivity. Finally, we can use perennial crops' ability to provide habitat and shelter to wildlife to create corridors and other landscape patterns that support biodiversity. And next slide. Our work to date has focused principally on water quality, and so I will focus most on, for my presentation, most on water quality. What you see on the slide is an example of a sustainable land intensification strategy to achieve both bioenergy and water quality. For instance, land that does not drain efficiently or is frequently flooded presents risks in growing row crops. However, deep-rooted short rotation woody crops or deep-rooted grasses really don't mind being on wet ground as much as row crops, and so they could be a much better option for this land. If on top of it we could capture the nitrate from the adjacent row crops that go through subsurface flow and use it to enhance the growth of these woody crops, bioenergy crops, it would be a win-win situation. We have an integrated landscape which can provide sustainable and sustained energy, improve ecosystem services, and actually be more profitable for the operator of that particular field. Next slide. When we talk about marginal land in general, we mean, for these purposes, we mean several different types of land. And what I would like to stress is that farmers and farm operators know very well where that land sits on their farm and know much better what fits this category than anybody else. But for our purposes, I will just mention a couple. Land that carries a lot of erosion potential. Land that's on a ridge and therefore is droughtier and perhaps more difficult to cultivate with water-intensive plants. Roadway buffer, riparian and contour buffers. Land that floods or stay very, very wet, doesn't drain very efficiently. And every farmer knows those pieces of land where no matter what you plant, there's always going to be a large puddle and no crop growth. And this is the land that we are really trying to target in our landscape design. Next slide. Erica, if you could go back one. Thank you. Going back and exploiting these variations in soil properties across a field, the important thing is that the granularity of the sustainability of land for a specific purpose never really follows field borders. Subfield variations in soil conditions determine environmental impacts and farm revenues. You can see on this slide two example maps from our experimental field site in central Illinois. So this is a 16-acre field, and you'll see that there are really two main conditions in this field. The first one on the top, and you'll see the green part in that yield map, which is a floodplain, fertile, comfrey loam, which provides high yields, which is the green area. And in the adjacent map, you'll see the blue area. It provides little nitrate exports. Very little nitrate leaves this particular piece of the field. Again, in the same land, the lower portion that you see in yellow and brown is the less fertile, more permeable silt loam, which provides reduced yields, and in the other image, much heavier nitrate losses, which are represented in yellow and red. So we also know from our colleagues in Idaho that areas that are sensitive to grain prices are a good candidate for bioenergy to improve farm economics. And other considerations may come into bearing in allocating land for particular uses. Risk reduction, for instance, flooding, drought are events that may hit or miss and play definitely a role in the probability of success of a crop. And so the strategy is really to find that sweet spot where we can maximize the economics and minimize farm inputs and nutrient losses at the farm level. And if we follow this train of thought, if we deliberately grow crops for dual purposes, for bioenergy and for ecosystem services, there is a really beginner of a hook to think about acknowledging ecosystem services and actually provide some form of quantification of them at the very least, if not outright compensation. Next slide. So is there enough of this land so that if we plan on using this land, do we have a chance of being relevant and providing a step forward? We did a simple analysis in 2010, and we looked at the main Midwest row crop corn belt states. And it provided that in comparison to simple conservation reserve program land, there is a lot more land which is in this condition of being either riparian or roadway buffer or other type of marginality. So there is actually potentially a good chance that actually this would be a much easier and better choice of land to grow bioenergy crops in. Next slide. I will then describe a case study that we have been working on in central Illinois. And we toggle between the field and the watershed scale. This is a small watershed, about 50,000 acres in central Illinois. And the reason why we are working at this scale is because this is really the scale at which a decision about implementations are being made by the farmer or farm operator for the field scale, and by conservation groups and watershed alliances at the small watershed scale. So it's a really, really important scale to test not only the system, but how it is acceptable and how it actually can play out in the future. The Indian Creek watershed, which is the one you see depicted here, is a tributary to the Illinois River, which eventually flows into the Mississippi River. And you have seen in the maps before how yields and nitrate exports is influenced in this particular field site by soil types and soil conditions. Next slide. So we've set up a field trial of a buffer that at the same time produces biomass and improves water quality in this field. And before we even had the final blueprints, we did a lot of work in setting the baseline to understand where it would be best located. We developed several thematic maps analyzing site conditions. And as you can see from the results of this work that I've shown in the slide, a riparian buffer would not really have been of much use in controlling nutrient export in this case. And I should argue that this case is hardly unique. The second top image there shows flow path lengths, and you can see from there is relatively little of the runoff that actually goes towards the riparian area, which is to the left of the jagged contour to the left where Indian Creek is. Most of the flow path really concentrates towards the center of the field. The next image shows the hydrological model of groundwater flow, which flows parallel to the creek. You've seen the yield map and identified where the areas of higher productivity and lower productivity are, and you also seen the maps below that show the highest losses of nutrients. You can see from this that a riparian buffer along the Indian Creek borders would really not have contributed too much to the improvement of water quality benefits. However, a buffer that runs along the straddles the two soil types would actually be much more effective in controlling and scavenging off the nutrients before they actually have a chance to move with the groundwater or be transported elsewhere. Additionally, this is an area where the economics would actually be more favorable for the farmer to actually drop corn because it's not really sufficiently productive and try something different, which is an interesting concept for switching. Next slide. So a buffer of willows was planted right there between the two soil types in 2013 following this design. And this coming summer, will be in the third year of growth and therefore ready to provide results about the root penetration in the subsurface flow path and the impact of this buffer into mitigating nitrogen flows. While we're waiting for the roots to develop at the right depth and the trees to be big enough to make an impact in the field, we have been working on modeling what we think are the potential impacts of this buffer. And we've used DNDC, a biogeochemical model simulating nitrogen fate in this field. And we use that to predict both leached nitrate and nitrous oxide emissions from this field when growing a buffer, alternatively a switchgrass and willow. We tried two cases. As you can see from this image, results predicted a substantial removal of nitrogen leached and a measurable and important decrease in nitrous oxide fluxes from the system in itself. We also calibrated the model against field-measured corn yields and willow yields from appropriate literature, waiting to have the actual data from the field to fully validate this model. Next run, I'll give you just a few images of the willow planting from top right counterclockwise, the planting of the willows back in 2013 through growth, the first year of growth, and at the end of the last growing season. As you can see, the last image there shows the willows against corn, which is just being harvested. And I wanted to share these with you because these images are really very important in working with the farming community and the operators of the fields and those who make decisions in trying to assess how well the system works with their logistics and their farm operations. So there's more than a picture in this image. But the next slide shows some of the environmental monitoring activities that we are carrying out to this day, including the greenhouse gas fluxes, water collection from about 4 to 5 feet below ground where the subsurface flow is going on, and the growth of the willows in the middle of the corn fields. Next step, next slide, we have been working on understanding if we scaled this concept up to the watershed, what would be the benefits. Obviously, as I mentioned, the watershed is important as a scale because it's really where we have the cumulative and holistic view of the benefits that integrate bioenergy crops and ecosystem services deliverance. We wanted to determine if we deployed in a watershed, what would the benefits of this design. And so we looked at different kinds of land properties as the basis for watershed design. We looked at marginal land classification, and the caveat is that marginal is really a very tricky term to use, very difficult, and it depends really on the objectives that we have for our work. In this particular case, by marginal, we really mean not only at lower productivity farmland, but also farmland in the watershed that is susceptible to leaching nitrate, has poor drainage, floods frequently. All these combinations of marginality alone or in combination with each other, or is otherwise more vulnerable to environmental externalities in general. In this slide, you will see all the categories summed up in one slide to the left, in one image to the left, and in the right figure, the areas that are higher at risk for leaching nitrate towards subsurface flow. So there are very specific areas which have particular soil conditions that are more amenable to losing nitrate. And when we put in the next slide this particular area into a different landscape design, as you can see here, that we used SWOT to simulate what this new design would provide as far as benefits. So in the top row figures, you see the business as usual with the usual land use, and in the right side, you see the same area except with marked in red areas where we would deploy switchgrass, for example, in the watershed as a means to control water quality. For each of the two conditions, you see in the bottom row of maps the impact respectively on nitrate losses and on sediment losses. You can see the before and after, or the business as usual versus landscape switchgrass design, the benefits that can be achieved in both nitrate leaching and sediment are pretty visible, and you see them in a difference in color. The lighter the color, the lower the loading. Overall, this presents a promising picture towards acceptance and the utilization of this design. Next slide. We've looked at projecting crop productivity and water quality in the watershed based on that design. And we also compared two different cases. One is using underproductive land, and one is using vulnerable land, the land I mentioned to you before. From this comparison, we see that while productivity of the acreage in corn is substantially unchanged, in either case, in other words, the higher productivity in terms of megagrams per hectare is not impacted, the biggest environmental benefits and changes in productivity of each crop are found in the conversion of the vulnerable land. And this is in part because in a watershed like Indian Creek, underproductive land doesn't represent a lot of the land that's there. Overall, productivity per acre changed little in the vulnerable land case as well. What really changed is the environmental benefits, as you can see in the yellow columns within the bigger column. To the left, you have a different visualization of the impact, with also showing the water yields change based on different crops and different land allocation, which go from close to 0 to about 10% on average. With that, willows are the more water-intensive plants compared to switchgrass. And last but not least, I just wanted to mention that all this is good and fine, but it's really important that it gets vetted by the people who actually are going to be implementing all this in the field. So I want to touch on how we have been going about allowing ourselves to have a broader discussion with players that will adopt this in the future and really have a two-way conversation on what would be the most appropriate way to do this. So with help from our colleagues at the University of Michigan, we have held several workshops, and we have used a variety of tools to work with the agronomist and farming community and farmer support community in the Indian Creek watershed, and presented them with maps, with field conditions map and soil elevation maps, visualizations and site visits, as you can see portrayed in the picture in the slide, and altogether we've been brainstorming about how these interplanting and these combined row crop bioenergy crops could be playing out in the field. And we were grateful to the students, the grad students at the University of Michigan who have really good drawing skills to instantly record ideas and thoughts into very usable formats. And this is through this kind of interaction that we really can refine our analysis and our work in ways that are directly applicable. So this was the first step towards expanding the discussion besides the research realm with the base who is going to be implementing. The next part of it, as Virginia mentioned, and it's going to be in the next slide, is really convening a broader community of people from researchers to government to nonprofits, industry, regulators, farmers, and everybody else to actually start discussing and starting a broader level of dialogue. And we did that through 2 workshops that the Bioenergy Technologies Office organized last year. There were many take-homes from these workshops. We had some positive outcomes. First of all, landscape design is to include bioenergy crops is a desirable way forward. And we also, I think, agreed that there is a considerable knowledge already present from different disciplines that can be brought to fruition in an integrated effort. So we have some bases covered. We need to do more, but we have a really good starting base. We also agreed that any way that will incentivize the implementation of these systems may be much better than other ways to force a system like this into realizations. Obviously, it's not all clear to go. There's obstacles to be addressed. There are risks associated with growing bioenergy crops and implementing landscape design, which need to be reduced. Just to mention one that was really discussed thoroughly was crop insurance. Is there crop insurance for bioenergy crops? Do we have the data to support crop insurance for bioenergy crops? We did markets for the biomass produced in general, which are lacking in many parts of the country. Discussion about the ecosystem services highlighted the uncertainty that we have about the value of these services and the fact that we are starting to get tools for assessing them, assessing productivity, logistics, and the practicality of some of the approaches. We also identified land ownership issues. If the agricultural world and the row crop land goes towards short rental agreements, there may be a conflict with perennial crops because typically one-year agreements are not what it needs to be obtained for perennial crops. There's also a lack of incentives to minimize planting or fertilizing in areas that are risky or underproductive. And we also need to address a very important issue of polycultures. Unless landscape design could include polycultures, there were questions about how biodiversity may not really indeed increase. One monoculture would be simply substituted for another one, and therefore we really need to find better ways to bring polycultures into the whole supply chain for bioenergy. Several activities were recommended: case studies, addressing supply chain obstacles, developing know-how, and more than anything else, to promote broad partnerships and integrate the research with the broader stakeholder community. So we've started this discussion. I would like, in closing my presentation, to invite you all to contribute to this dialogue. If you have any ideas or any important consideration for this, BITO has established a LinkedIn group, and we'll be able and be sure to circulate that link to participants in this workshop. So my presentation is over. I just have one slide to acknowledge all the many people who helped us come to this point, from student interns to landowners to the local county Soil Water Conservation District and NRCS officers, Conservation Technology Information Center, University of Michigan, Gayatri Gopalakrishnan, and Indian Creek Watershed Project Leadership and Sponsored, and Eric Rondon, Harold Ruiz, and many others who provide realistic input every day. Thank you very much.
Thank you so much, Christina, and thank you also to Virginia. Both of your presentations were great. So we'd like to leave you all with a couple important takeaways from today's webinar. Bioenergy is not one size fits all. It should be considered as part of a portfolio of energy efficiency and renewable energy options. And improving sustainability requires reducing energy use as well as designing and deploying energy systems that are well suited for a particular context. So we hope that you take away from today's presentation that through design we can intentionally enhance sustainable outcomes from bioenergy systems. So thank you again for joining us today. And as I mentioned before, the slides will be made available on the Bioenergy Technologies Office website. And please direct any questions that you have to this email address shown up on the screen. And we ask that you please include biofuel sustainability in the subject line of your email. So at this time, I'd like to thank all of our attendees for joining us today, and I hope you all have a great day. Thank you.